folks, welcome to Related Rates Part 4. So today we're going to look at an example that looks at a right cone, and this is going to use some of our similar triangle stuff that we learned from the shadow problem, okay? But let's read through the problem first and then come up with a diagram and then come up with some formulas. So consider a right cone that is leaking water. The dimensions of the conical tank are a height of 16 feet and a radius of 5 feet. How fast does the depth of the water change when the water is 10 feet high if the cone leaks water at a rate of 10 feet cubed per minute? So before I draw my diagram, let's get some color coding underway. So I'm going to say that things that are dealing with the height, I'm going to use red. And so let's see, the height of the tank is 16 feet, but the height of the water is 10 feet high. And then with the green, I'm going to say the radius is 5, and I don't think I have other information about the radius. And then for the volume, I'm going to use blue. Now, some of you might be asking, how did she know that that was volume? And a lot of times I actually go based off of the units. And so I know that feet cubed is a unit for volume. And so what I actually have here is that dV dt equals negative 10 cubic feet per minute. Now it's going to be negative 10 because the tank is losing water. Water's coming out of the tank. Okay. Now let's get our diagram started. So I'm going to go ahead and draw a cone. Okay. And I know that the height of this cone is 16 feet. And I know that the radius of this cone is 5 feet, and I know that it's filled with water. Now, I'm actually going to draw a second cone that represents like the amount of water that's in the tank at the time we're looking at. Now, it's going to be shorter because the height of the water is only 10 feet in the tank, okay? And the question is asking us, how fast does the depth of the water change? So they're actually asking us to find how the height is changing over time. Now, it would be super nice if we could figure out what our radius here equal, because I can't label that part of the diagram yet, okay? But let's do this. Let's come up with our volume formula for a cone and then go from there. So volume of a cone is 1/3 pi r squared h. Now I'm going to go ahead and start this problem in one way, show you why we can't do it that way, and then go back and do it a second way. All right, so be patient here. Now, if I wanted to find my derivative of v, I know that the derivative of v is dv dt. And I might also notice that this 1/3 pi is a constant. So I can put the pi over 3 in the front. Now, when I take my derivative of this part, this r squared h, I'm actually going to need to use product rule. And so I'm going to go ahead and set that up off to the side. So u equals r squared, du would equal 2r dr dt, and v would equal h, and dv would equal dh dt. Now keep in mind that because we're doing related rates, everything has to be something dt when we're looking at derivative. So let's plug that into our product rule. We're going to get u dv plus v du. Now if this were my formula, let's see what numbers we actually have. I know I have dV dt because that's that 10 cubic feet per minute. I also know that this constant in the front is just going to stay, so I don't have to worry about that. I know that the height is 10, so that's fine. And I realize now that there's a lot of other stuff I don't know. I don't know what the radius is. I don't know what the dr dt is. I don't know what that radius is. But somehow with this formula, I would be expected to find dh dt. And so we're almost stuck here because we have too many variables and not enough information. Now, for those of you who are planning on going all the way through Calc 3, you're going to learn another way to do this problem where it's going to be okay if you don't have all that information. But for right now, we're going to have to think about how do we redo this problem in a way that we can solve with the information we're given, okay? So let's start over. We'll keep our diagram, we'll keep our formula, volume equals pi over 3 r squared h. But here's what I'm going to do. I'm going to use this idea of similar triangles. That's why I drew the two cones in the beginning. And I'm going to set up a ratio, okay? And so what we're going to do is we're going to say the radius over the height in the cone is always going to be of the ratio 5 over 16. Because if I look at the original cone, the radius is 5 and the height is 16. And no matter how much water comes out, the ratio between the height and the radius will always be 16 to 5. And I'm going to do a little bit of substitution because I have enough information to deal with the height, but I do not have enough information to deal with the radius. So I'm going to try and get this formula to have no more radius, and then I could solve it using what I know about height. So radius would equal 5 over 16 times the height. And so I'm going to use that everywhere I see an r, I'm going to put 5 over 16 times height. So this will give me pi over 3, 5 over 16 h squared times h. And so this is just another way of saying r. Okay, so let's simplify this equation a little bit. I've got pi over 3 times 25, that's 5 squared. And what do we get when we do 16 squared? We get 256 height squared times the height on the outside. And so this is going to give us 25 pi over 768 h cubed. Okay. So let's see what we have for our volume formula. We have volume equals 25 pi over 768 h cubed. Now, if we had this formula, let's take our derivative and see what that gets us. I get dv dt equals. This looks intimidating, but it's a constant, so I can keep it out in the front and just take my derivative of h cubed, which is 3h squared, dh dt. Okay, now let's see what information we have from our original problem. We have our dv dt. This is a constant, so we know those numbers. They gave us the height as 10, and they asked us to find dh dt. So this is really good because we have every single number we need except for the dh dt, which is what we want to find. So let's fill in those values and see what happens. Okay, we've got -10 equals 25 pi over 768, 3 times 10 squared dH dt. Okay, let's see what this gives us. So I have -10. I'm going to multiply the 768 to that side. I'm going to divide by the 100 and the 75 pi. And that will give me my dH dt. And when I calculate everything out except for the pi, I'll get -1.024 over pi. And we're looking at feet per minute. Okay, so let's review what this actually means. That when the water is leaking, or when the volume goes down by 10 cubic feet per minute, and the height of the water is 10, then the height goes down by -1.024 over pi feet per minute. Okay, I'm going to zoom back out so you can see the whole screen. Give you a couple moments to look that over, and we're going to stop here for part 4 and come on back for part 5 and a few more examples.